This is the second lecture on correlating networks. So far, we have learned three different measures that can capture the correlations between the degrees of a pair of nodes connected by an edge. So as the first measure, we learned the matrix element E sub jk, that is the probability to find an edge whose two end nodes have degree j and k. So this is the most comprehensive measure in a sense that it counts all the possible combinations of degrees existing in a network. And by observing the distribution of this probability, we can tell if the network is associatively correlated or disassociatively correlated or no correlation at all. As the second measure, we also learned the average nearest neighbor degree, KNNK. Okay, so if you focus on a node with degree k, by counting the average degree of its neighbors, you can come up with this two-dimensional plot. Okay, if this function KNNK shows monotonically increasing behavior, like shown in the left panel, it indicates the associative correlations. On the other hand, if KNNK shows this decreasing behavior, you can say it is more or less negatively correlated or disassociative. As the final measure, third measure, we learned a Pearson correlation coefficient R. So some people call it just simply associativity. So this number is limited between -1 and +1 because it is normalized. And it's very handy and simple. It's simplest out of the three, but the simplicity comes at the cost of the information that is retained in the previous two measures. Okay, so depending on your purpose or your analysis, it may be okay to use the value R, but in other times you might want to use the other measures of correlations. Okay, now we delve into the origin of this degree correlations. So we now have a scale-free network generated by a configuration model. I didn't tell much about the configuration model, but this is in a sense a Erdős-Renyi type protocol to generate a scale-free network. So simply put, you are given a number of nodes whose degrees are already determined. Okay, so all the nodes have its own number of connections, but they don't have the detailed list of their connecting partners. Somehow you have to satisfy the matching between the nodes to complete the process of generation. Okay, so the question we will ask is the expected number of edges between arbitrary nodes. To be specific, we are focusing on these two hub nodes whose degrees are 55 and 46 in this example. And according to the previous calculations on the uncorrelated network, so if you assume no correlations at all, then the expected number of edges between these two hub nodes should be somehow more or less 3. Right? But if this network is to be neutral, we require 3 connections, 3 edges between these two nodes. But in order for this network to be neutral, we have to allow for multiple edges, which is not the case. Right? So as long as we stick to a simple connections, simple graph, where the multiple edges are not allowed, then we cannot we cannot finish this matching process. So this network cannot be neutral. Okay. This can be explained by looking at this simple model system. So we are given, let's say, for 13 nodes with degree 1 and one node with degree 8 and one node with degree 7. By matching the edges, unfinished edges between the nodes, somehow the 13 nodes with degree 1 can find its kind of binding partners, but the two hub nodes somehow have lost one connection. Lost meaning it doesn't find any good match. So it is indicated here in the broken lines. So there's no way of satisfying this connections, right? So this is actually the underlying reason why we observe negatively correlated network in many scale-free networks. Okay, to further the question of on the maximum number of edges between a node with degree k and k prime, now we recall high assortativity means higher probability of direct connection between the two hub nodes, right? But as long as we allow only one link, as long as we stick to a simple graph, then we can simply run out of hubs to connect to each other to satisfy the assortativity criteria, which was a neutrality criterion in the previous slide, right? So again, according to the previous neutrality condition, we expect this many number of connections between the two nodes with degree k and k prime. But in reality, the maximum number of edges is limited if you consider this simple network. So here we have 3 nodes with degree 3, okay, 4 nodes with degree 2, and we try to kind of match by linking each of the stubs, right? So how many connections, how many edges are possible between the two groups of nodes, which has degree 3 and 2? So that is definitely capped, limited by the total number of stubs that are emanating from the nodes with degree 3, which is here 9, right? 9 is coming from 3 times 3, right? And also it is limited by the number 8, which is 2 times 4, capturing the total number of edges, stubs, emanating from the node with degree 2. And another limitation comes from the possible combinations of kind of complete graph, complete bipartite between the two groups of nodes, right? So here, the number of possible pairings is all the possible pairings, regardless of the degree, is given by 12. But if you compare it to other situations where the degrees are higher than this, let's say you have degree 11 and 12, then the possible possible connections might be much more than this, right? So in that case, the product of the number of nodes can be a limiting factor sometimes. So overall, the maximum number of connections between the two groups of nodes is limited by this formula, okay? As long as we don't allow for multiple connections between any pair of nodes. All right. So neutrality may not be necessarily a trivial thing to achieve because of this skewed degree distributions. So if we introduce the quantity of a fraction of edges between the two groups of nodes with degree k and k prime, so that is basically the ratio of the expected number of edges to that of the maximum connections, okay? So neutrality condition require allows us to rewrite EKK prime in the numerator as again n times the average degree times the probability EKK prime. So if we work out this formula, we come up with this final expression. So that is proportional to the product multiplication of two degrees k and k prime. Okay. But when the restrictions of simple edge is to be felt, that is to say, when a degree of one group of node is larger than the total number of the other group, and vice versa, then this ratio, fraction, should be less than 1. Okay? That is implying that the Ks here, the quantity Ks, is approximately proportional to the square root of the average degree K. Okay? So the network neutrality is not trivial in a sense that the neutral network cannot have nodes with degree larger than Ks, which depends on the total number of nodes. Okay, so if there are nodes with degree K which is larger than Ks, we cannot find sufficient links between the highly connected hubs. That is exactly the situation we have seen in the previous slide, right? So in this plot, there is a region shaded by dark gray where the RKK is bigger than 1, which is actually prohibited by construction. Okay, so in this sense, this hyperbola RKK prime is equal to 1 defines the structural cutoff. So simply put, a node in this network cannot have this fraction of connections. Okay, so how to get around this? Okay, so the simplest solution is probably we do not allow nodes with degree K which is larger than this structural cutoff. Okay, so even in the scale-free network, we can limit the maximum number of degree that is assigned to each node. Okay, and second one is just let the nodes have let the networks have dissociative correlations. Okay, leaving fewer links between hubs. Okay, so that is the underlying reason why not the most, but many of the scale-free networks comes up with negative correlations. In that sense, the social network is quite unique. So we already aware of the fact that most of the social networks show pretty assortative correlations. So that was actually an active research topic in recent days. Okay. Now we recall the previous lecture on the natural cutoffs in scale-free networks. If you remind yourself of this lecture note 4A, simply starting from the requirement that the number of nodes, the fraction of the highest degree node should be of order 1 over n. So that is almost a defining relation. So starting from this simple relation, you could come up with the relations between the maximum degree and minimum degree and the exponent of the power law degree distribution. All right? So if you apply the previous conclusion to this, then you can come up with structural cutoff Ks is now related to the number of nodes and the average degree of the network. Okay, so in large scale networks where the number of nodes is much larger than 1, especially for the degree exponent gamma, which is higher than 3, then Ks is simply larger than or equal to K max. So you don't have to worry. Okay, already K max is kind of cutting off. Okay, so that no nodes would have degree more than K max. Okay, so you don't have to worry about this structural cutoff. So no nodes for which EKK is larger than 1. So there's no conflict between the degree correlations and requirement of simple graph. So you can construct a power law or scale-free graph with neutral correlations. But the story becomes more sophisticated, complicated, if the degree exponent becomes less than 3. Okay, so you start to feel the structural dissociativity. Okay, so this negative correlations between the neighboring nodes degree is actually coming from the power law. Okay, so that's the underlying mechanism to explain why we observe dissociative correlations in many scale-free networks. Okay, so actually if we construct a scale-free network where the network size is 10,000 and degree exponent is given by 2.5, which is smaller than 3, then you can observe this Kn and K behaves like dissociative networks. As you see here on the right panel, the functional form of Kn and K shows more or less monotonically decreasing function of K. All right? But as long as you allow for multiple connections between hubs, then this negative correlation disappears, as you see in this second row panels. Another way of removing this kind of spurious correlation is to introduce the cutoff in degree, maximum degree, so that you will have this structural dissociativity gone by imposing the cutoff for the nodes with degree K, which is larger than the structural cutoff value Ks. Okay? Now the question is whether this apparent dissociativity observed in scale-free network stems from a structural dissociativity, or it reflects any genuine underlying mechanism of network formation. Okay, so to answer this question, we introduced the degree preserving randomization, which is given like this. So we are given 4 nodes here, A through D, right? So it originally had degree 4, 3, 3, 2. But the link between A and B has been switched to the link between A and C. Likewise, the link between C and D is now diverting to another link between B and D, right? So throughout this procedure, we didn't change the number of degree, the degree of each node, right? So we preserve the degree distribution, but we change the connecting partners. In that way, we may change the degree correlations, right? So this is so-called degree preserving randomization, okay? Pick up the 2 arbitrary edges and switch the binding partners or linking partners arbitrarily, okay? That is the mechanism of achieving this randomization, okay? So if you look at the left panel, that is for scientific collaboration network, this is part of social, sort of social network. So it is presumably strongly assortative network, which is actually the case according to this wasabi colored scatter points, right? But by applying this randomization procedure, this network is now converted to a neutral network. As you see from green squares and purple triangles, right? So what does it mean? The empirical network itself was shown to have positive correlation, assortativity. But after this randomization, that assortativity is gone. What does it mean? Right. This assortativity is not from any constraint due to the scale-free degree distribution. Okay, so it's a kind of genuine correlations. The middle one, the power grid network, is originally neutral because Kn and K shows more or less constant behavior. And after randomization, still it shows a neutrality. That means, yes, power grid is truly a neutral network. Okay, but if you look at the metabolic network, the biological network, it showed a negative correlation, disassortativity originally, right? And after randomization, still you see from this yellow, green squares, you see negative correlation. Even though we randomize the linking, is still this negative correlation persists. What does it mean? Yes, as you correctly guessed, this negative correlation is coming from structural disassortativity. Okay? Yeah. So by randomizing the empirical network, you can tell whether this apparent assortativity or disassortativity is actually coming from the genuine origin or is simply reflecting the structural constraint that is required by the power law degree distribution. All right? So the most empirical networks observed in the real world shows either structurally induced disassortativity or structure independent, the power law independent assortativity, which is the main signature of the social networks. So to summarize, the most real-world networks display degree correlations. So it is hard to achieve neutral network, okay? Yeah. Except for the power grid. Power grid is truly neutral, which is the only truly neutral network. And all networks that display disassortative tendencies, email, protein, metabolic network, do so thanks to their scale-free property, okay? So this disassortativity was kind of induced by the constraint of power law degree distribution. On the other hand, the assortative networks cannot be explained by the scale-free degree distribution. Most social networks belong to this class, and so this is truly reflecting a certain growing mechanisms which is not present in other technological or social networks. All right. Now the summary of degree-degree correlations. No multiple edge is allowed in simple graph, and because of the existence of hubs in power law graph, random connections of nodes lead to unavoidable disassortativity. This is so-called the structural disassortativity. Okay. For a neutral network, structural cutoff is given by square root of the size of the network times the average degree. So if you really want to construct a neutral, uncorrelated network in models, you have to either introduce an artificial cutoff in the network, or you have to keep in mind that even though you're randomly connecting the stubs by imposing the constraints on the edges, non-trivial correlations will emerge. Okay, so network, the structural dissociativity is a kind of default. Okay, and in empirical networks, the question was, the degree distribution, is it sufficient on its own to describe the structure of a network? Are the nodes really randomly connected? So in the case of assortative networks, the correlations are attributed to some genuine origin. Okay? But on the other hand, in the dissociative case, you have to be careful to check whether this dissociativity actually comes from the structural dissociativity or reflecting any genuine origin. Okay? So here are some more details on how to generate correlations, how to introduce your model network, how to introduce any synthetic artificial correlations into your model network to test your hypothesis. But I will skip these technical details along with other initial attractiveness model and Zuby, Brunet, Sokolov. These are all for the motivated physics majors, so I will skip this part. Okay, to summarize, there are three measures of degree correlations. The first one was EIJ or EJK, that captures the probability to find an edge whose two end nodes have degree I and J, or J or K. Okay, so that is the most comprehensive measure. And the second one was degree correlation function, or nearest neighbor degree distribution, or its average. Okay. And the final one was the assortativity constant, or Pearson correlation coefficient, limited between -1 and 1. Okay, so this concludes this lecture note 6, and I'll switch to lecture note 7 in the next lecture. But before I conclude the chapter and start discussing the community detection and clustering algorithm, let me point this out. We have discussed assortativity, or positive or negative correlation, only in terms of degree centrality, right? But as you can imagine, nodes can have different attributes, different properties. Especially in the case of politics, as you see here in this American politics network. So here nodes with blue indicate the person who is running his own blog is biased or leaned toward the Democratic Party, while the red ones are more favorable to Republican Party, right? So in that case, this assortativity is even stronger. Okay, so the left-wing, right-wing division is not only in this country, Korea, but also it's really prevailing phenomena across the world. So if we extend the analysis of correlations, not only limited to the degrees, correlations between political stance and correlations between something else, we can even analyze a much wider range of networks in terms of correlated networks. All right. this is the end of the lecture, and the remaining part is a technical algorithm that help you generate a network with a specified distribution of EJK. So again, if you are motivated students of physics, then yeah, you can follow this content. All right, I'll see you in the next lecture.